Good morning. So I am very pleased to welcome our first candidate talk for our research assistant professor opening in natural hazards. And as part of that, I'm really happy to welcome Dr. Tyler Pelle to join us at the Institute today and yesterday. So he comes from the Scripps Institution of Oceanography, where he is a Green postdoctoral scholar. And then prior to this, he did his PhD in Earth Sciences at the University of California in Irvine, and his undergraduate work at the State University of New York in Oswego. And his work focuses on using coupled ice sheet models to understand the interactions of the Earth's ice sheets and glaciers with the broader climate system. And he does that with an eye towards understanding and reducing the uncertainty in sea level projections. And he's received several awards for his work, and this includes the Antarctic Science Bursary Award, which is for the development of promising early career scientists in that field. And he's also received the Richardson Medal of the International Glaciological Society for his work co-leading the ice sheet model intercomparison project. And then he's also been part of a NASA Group Achievement Award for his work developing an ice sheet and sea level model. And I'll just kind of wrap up the introduction by noting that he's really active in service and mentoring. And one example of that is that he is a trainer for bystander intervention training. And then with that, I'll just say, let's please join me in welcoming Dr. Pelle to UTIG.
Awesome. Yeah, thank you so much, Krista. And yeah, thank you all for the really, really warm welcome over these last 2 days. It's been really fantastic getting to meet so many new faces and other people I've been working with for a little while now, but remote, and just learn about all the fantastic research you all do here. So I'm really excited to share some of the work I've been conducting over the last few years now, which is using coupled ice sheet modeling to investigate how the subglacial environment, ocean environment impact a large sector of the East Antarctic ice sheet over the 21st century. So I wanted to start my talk by showing the schematic of Antarctica. And so on this figure here, over the ice in that white to blue shading, you're seeing the surface ice velocity. And then over the ocean on the continental shelf in that red to blue shading is the, I believe it's the bottom ocean temperature in degrees Celsius. And the main part to get from this picture here is that there's some sectors of the Antarctic coast that are experiencing warm waters circulating on the continental shelf. In particular, there's the Bellenhausen and Amundsen Sea sectors here along West Antarctica. And then this more dull shade of blue here is a little bit of warm water as well, focusing on the coast of the Aurora and Wilkes subglacial basins. So if we take a look at current rates of Antarctic ice sheet mass loss from GRACE from 2002 to 2020, you'll notice that, well, it's not really a coincidence that where we have warm water circulating on the continental shelf, we also have high rates of Antarctic mass loss. Again, in particular, there's really strong rates of mass loss in the Amundsen Sea sector, where we have some pretty notable glaciers, such as Thwaites and Pine Island that you might have heard of. And then also there's some sectors as well in the Aurora Subglacial Basin. You'll notice this little blotch of orange there as well. And so the ocean is the main driver of this mass loss. And so to understand what's happening there, I'm going to take a look at just an idealized vertical cross section through an idealized ice sheet ice shelf system. And I'll kind of run through it. So on the right-hand side of the screen here, we have the ice resting directly on the bedrock below. So that's grounded ice. And so the ice in this figure is kind of flowing towards the right of the screen. So there's a transition point where the ice lifts off the bedrock and begins floating. So that's what's known as the grounding line. And then this floating extension of the glacier is what we call the ice shelf. And so warm ocean currents circulate on the sea floor, and then meander into the sub-ice shelf ocean cavity, which is that oceanic region below the ice shelf. They upwell at the grounding line and then induce melting along the base of the ice shelf from the grounding line up to the point where a buoyant current loses its buoyancy, or where we reach the front of the ice shelf there. And so this process is important because ice shelves almost act as like dams that hold back this upstream flowing into the ocean. And so So if we thin that ice shelf, or if we weaken that dam, this ice can flow more easily into the ocean, and that would constitute a sea level rise contribution. And so that's why it's a process that we are continuously concerned about for Antarctica. Of course, the Antarctic ice sheet doesn't just interact with the ocean. There's also some other boundaries that drive its dynamic evolution as well. And the one that I'm going to focus on a bit in this talk is the subglacial environment. And so recent studies have found that between the grounded ice sheet and the underlying bedrock, there's large quantities of fresh water that can become channelized and then flow out towards the coast of the continent beneath dynamic ice streams. And so in this figure here, we're showing the subglacial freshwater flux, and where you see the shadings of red, that's where there's predicted channels of fresh water. So to get a bit of a better idea of what's happening, I'm going to zoom into this large sector of the East Antarctic ice sheet. So this is the Aurora Subglacial Basin. It's a really large glaciated basin in East Antarctica that contains, I believe, over 7 meters of sea level rise potential in ice. And also contains some very notable glaciers that I've been working on to study over the past few years. And so in particular, we have Totten Glacier down here, Vanderford Glacier, which just wraps right around there, and then Denman, which is located on the upper end of the Aurora Subglacial Basin. And so in this figure, those yellow lines, those thick yellow lines, are denoting flow paths of subglacial water. And for the Aurora Subglacial Basin, sometimes these flow paths can, well, these subglacial channels can extend hundreds of kilometers from the interior of the ice sheet. And importantly, in many cases, these channels drain across the grounding line and into the sub-ice shelf ocean cavities that act to hold back these glaciers from flowing into the ocean. And so because there's a new input of water into that sub-ice shelf ocean environment, that can impact basal melting. And so looking at that same idealized cross-section, it's just a really simplistic view of what's happening. But we have the same fields plotted, and then beneath the grounded ice sheet and the underlying bedrock, we've added a subglacial freshwater channel. And so again, that water is carried from the interior of the ice sheet all the way out to the coast. It discharges across the grounding line, and then it can locally enhance turbulence near the grounding line water mass. And so that can entrain more warm water into that mass and locally enhance melt at the grounding line. And so this process is known, it's already known to occur, but we just don't have an understanding of whether or not it's important on glacial timescales. We are worried about it because the grounding line itself is the last contact point between the glacier and the bedrock. And so any perturbations and forcing that happen at the grounding line can have cascading consequences on glacier flow upstream. And so we believe that this is probably important, but we're ultimately not sure. And there's been other studies that have inferred that this process is occurring. This is from a paper by Wei et al. In 2020, where they modeled, or they inferred that there's this basal melt rate enhancement process occurring under the Getz ice shelf in West Antarctica. And so what you're seeing in this figure on the bottom are modeled subglacial channels. So those are going to be like those blue vertical lines there. And over the ice shelf, in that blue to red shading, is a melt rate difference, where essentially wherever you see red shading, it's inferred that subglacial meltwater is driving enhanced melt rates. And so in this paper, they found that wherever they had modeled channels, they also tended to have enhanced plumes of melt rates beneath the ice shelf. And so we have an idea that this is most likely occurring across Antarctica, but it hasn't been included in models. And there's a few reasons for this. The first is that Antarctic ice shelves can be really, really extensive, the orders of hundreds of kilometers. And so and what you're seeing in this figure here is all the Antarctic ice shelves are covered around the continent there. And so it's very costly, it's hard, it's also very, can be quite dangerous to try to access Antarctic grounding lines. And so we don't have great processes, or we don't have great observations to constrain this process. In addition, another way we could include this process in future model projections is to couple to an ocean model that can resolve the sub-ice shelf ocean cavity. The tricky part here is that subglacial discharge channels can have diameters of tens of meters, possibly. And so if we wanted to include this in an ocean model, we would need to have its resolution be around that. And so to run an ocean model of that resolution on glacial timescales is just not, it's not going to be possible. And so what we typically do in this case is that we will develop a parameterization of this process that is a lot more cost efficient in terms of computation. And so, for instance, what this would look like is that the sub ice shelf melt would be some function of far field ocean conditions out here, the subglacial discharge flux here, and then we would be able to compute a melt rate underneath the ice shelf. The issue is that there doesn't exist a two-dimensional parameterization that can be run in ice sheet models of this process. And so that has been the goal of some recent work, is to work on that front. And so with all that introduction, in this talk, I'm hoping to answer the question, how will ice-ocean-subglacial hydrology interactions impact the evolution of the Aurora Subglacial Basin over the 21st century? And so I'm going to split the talk up into 3 sections. The first is I'm going to develop that two-dimensional parameterization of melt that can resolve melt that's driven by both the ocean and those subglacial water fluxes. In the second part, I'm going to take that parameterization, apply it in simulations of the Aurora Subglacial Basin at the 2100 to try to understand if what impact subglacial discharge and the ocean might have by 2100. And then also I'll talk about some ongoing and future research directions as well. So I'm going to start with the development of this parameterization. And its development is going to be focused on Denman and Scott glaciers. So I want to first talk about those and why they're exciting and why we focused on them. And so Denman and Scott glaciers are located in the upper end of the Aurora Subglacial Basin. And so we have the black outline here is denoting exactly where we are in Antarctica. And so in this figure over grounded ice, we're showing bed topography. And so it's going to be in that blue to brown shading, where bed topography below sea level is denoted by blue shading. Over the ice shelf, which is this large sector here that's shaded mainly in dull red, we're showing the satellite inferred ice shelf basal melting rate in units of meters per year. And then over the open ocean are ocean bottom temperatures from a regional ocean model I developed during my PhD. And so this model domain contains Denman and Scott glaciers, and these glaciers flow into this really extensive ice shelf. This is known as the Shackleton ice shelf. And unfortunately, Denman Glacier in particular has been thinning, retreating, accelerating since the 1990s. And so to get a better understanding of what's going on there, we're just going to zoom right into the grounding zone, which is delineated by this dotted black box here. So in this figure, we have all the same fields plotted, but we've also overlaid the 1996 and 2018 grounding lines as those dotted and solid orange lines. And so what we're seeing here is that between those 2 time periods, there's been a 5.5 kilometer retreat of Denman Glacier towards the inland part of the ice sheet, and that where this retreat is occurring, there are extremely high rates of basal melting. And so I think the maximum melt rate here is about 126 meters per year. And to put that into context, that was higher than any other melt rate that was inferred from this assessment. And so it is pretty clear that this forcing is what's driving this grounding line retreat. We're concerned about this because so we're right here, and upstream of Denman Glacier is this really deep continental trench here. This is the deepest continental trench on Earth that's been observed. And it is a cause for concern because if Denman Glacier's grounding line retreats towards the lip of that trench, which here we're seeing a vertical cross section through the main Denman trunk, if it's able to breach that trench, then it could lead to explosive grounding line retreat that ungrounds this ice that's extremely thick. And so that is the cause for concern. But ultimately, we need to understand the forcing that's driving that retreat if we have any chance of modeling how this glacier might evolve in the future. And so I'm showing the ocean forcing here simply to say that the ocean forcing that we've observed so far near Denman's ice tongue is not warm enough to be able to sustain these high rates of basal melting. And so we hypothesized that subglacial discharge could be contributing to this. And so that is why we focus on these glaciers. And so with all that said, the first thing we had to do to be able to model these glaciers is develop that parameterization that I talked about. And so to do so, we start with the base of an established melt rate parameterization that was developed in 2018 by Lazarums et al. And so this is a plume-based melt rate parameterization that it simulates buoyant meltwater plumes that rise along the base of the ice shelf. So the ice-ocean interface is this gray to blue transition here. And so we model plumes that initiate at the grounding line and then induce melt all along this ice-ocean interface. And so the plumes have a characteristic thickness, velocity, temperature, and salinity that are impacted by the entrainment of warm ocean water from below, the cold meltwater from above, and also on the geometry of the ice-ocean interface, right? So how sloped the interface might be and also how deep it is below sea level. And so there's a set of differential equations that govern how these four plume characteristics evolve in time. But the issue here is that as we tend towards the grounding line, the plume thickness tends towards zero. So melt rates are automatically assumed to be null at the grounding line. But this won't hold if there's subglacial freshwater draining from beneath the ice sheet. And so recent work by Adrian Jenkins and Donald Slater found that melt rates scale to about the 1/3 power of the discharge flux near the grounding line, near these subglacial outflow locations. And so in short, this is essentially how we set up our parameterization, where close to the grounding line, close to the subglacial discharge flux, we use this melt rate scaling. And then beyond some distance where ocean dynamics govern how the plume evolves, we use the Lazarums et al. Solution. And so this leads again to two regimes of melt. The first one is a discharge dominated regime. And so I just wanted to show the equations that govern this parameterization because they're pretty intuitive. So the first one, the melt that's driven by subglacial freshwater, it's a function of just some constants and then some geometric scaling terms that provide the melt rates, the proper scaling to the ice shelf geometry. There's the grounding line discharge flux to the 1/3 power. And then there's also a linear dependence on the ocean thermal forcing. The ocean melt regime looks pretty similar, but there are some key differences. Again, there's just some constants out in front, geometric scaling terms that have a very similar appearance to those up there, a quadratic dependence on ocean thermal forcing. And then we also scale by a universal melt polynomial that it scales the melt rates so they have the right similar values for what we expect to have in Antarctica. And then there's one key thing that we're missing, right? It's going to be that distance cutoff between those two regimes. Like, how do we tell when the plumes stop being governed by freshwater and start being governed by the ocean? And Adrian Jenkins came up with a solution for this. And in short, that distance is proportional to the grounding line freshwater flux, but inversely proportional to the ocean forcing. And this will probably all make a lot more sense spatially. And so this is just a similar figure that we saw before, where we have a sub-ice shelf cavity, and we also have the ice-ocean interface here. And so if there's subglacial discharge that initiates a plume that drives melting, the first thing we do in our parameterization is compute that distance cutoff. The next thing that we do is compute melting with the freshwater formulation between that distance and the grounding line. And then the next thing that we do is compute ocean melting beyond that distance. And so I wanted to show some results for some one-dimensional geometries. The first is a concave ice shelf where where we have the ice-ocean interface is this black line here. On the x-axis is distance from the grounding line. So 0 is the grounding line, and the far right-hand side of the panel is going to be the ice front. And then we're just showing depth on the y-axis. And so we have a concave ice shelf on the left, and then on the right is a centralized flow line through the Denman ice tongue that's been smoothed out a bit. And so for each of these geometries, I'm going to show melt results from what we call the full plume model. So that's going to be the solution from those 4 differential equations. And then we're also going to show melt results from our parameterization, which is just that simple 3-equation model that we had before. And then, so this is what some of those results look like. And so I'll run through what we're seeing here. And so focusing on the bottom left-hand panel here, again, on the x-axis is distance from the grounding line. So you can see where we are within that ice shelf cavity. The y-axis is the melt rate in units of meters per year. And so positive values are melting, negative is refreezing. And then we have a bunch of different lines. So the solid lines are the full plume model. The dotted lines are the parameterized melt. And then the color is just an increasing freshwater flux at the grounding line, where blue is no freshwater, so it's all ocean-driven melt. And then the red line is the highest freshwater amount. And so from these figures, I just wanted to get a few points across. The first is that, given how simple our parameterization is, we do an okay job at matching the full plume model results. You can see the general shape, focus on the concave ice shelf first, is the shape is very similar, where we're able to model, a relatively large melt rate increase at the grounding line from subglacial freshwater. And we also transition to refreezing as well. So our parameterization can handle both. In addition, for Denman Glacier, we have this black line here, our melt rate inferences from satellite imagery. And so when we don't have any discharge at the grounding line, we can only resolve melting of about 60 meters per year or so. But it's not really until we start ramping up that subglacial freshwater that we can start to resolve some of these really, really high rates that we see in the observations. And so ultimately, this is giving us a little bit of confidence, at least, that subglacial discharge could be a possible explanation for these really high rates of basal melting that the Denman ice tongue is experiencing. Of course, most ice sheet models aren't one-dimensional. They're plan view. And so while this one-dimensional model is great, ultimately, we have to extend its use to 2 dimensions to become useful for our purposes. And the way that we do that is pretty intuitive. So right now we're looking at an ice sheet, ice shelf from above, where the grounded ice sheet is on the left and the floating ice shelf is on the right. And so just like before, right, we have a discharge channel draining freshwater across the grounding line. And the first thing we do is compute that distance cutoff. But now instead of a point distance, we use it to set a circular radius around the discharge channel. And then just like before, within that distance, freshwater melt, beyond that distance, ocean melt. And we interpolate between. And so this is the same results. This is the results for the concave ice shelf, but now in 2 dimensions. And you can see, first you can see that distance cutoff. So I tried to match this idealized picture as best as possible. So you have the distance cutoff as this black dashed line here. You can see the melt rate enhancement from subglacial discharge, and then this is the ocean melting regime beyond. And so this discharge channel is parameterized to match the results from this red line here. And so you can see that if we just look right through the center of this figure here, that in general, the pattern matches with what we see in the one-dimensional case, where maximum melt rate of about 6 meters per year at the grounding line, and then it trails off to refreezing 200 kilometers away from the grounding line. And so this is, in essence, how we extend the application of this parameterization into 2 dimensions. And so now that we've done that, we can apply it to the Denman ice tongue with realistic ocean and subglacial boundary conditions. And so in this figure here, there's a few things going on. I want to focus attention first on the grounded ice. And so over the grounded ice, this gray shading is bed topography, but more importantly, the subglacial channels are modeled by this white to purple shading. And so one of our collaborators, Christine Dow at the University of Waterloo, ran the glacier drainage systems model over our domain to provide these outputs. And so in particular, under present day ice sheet conditions, we have a pretty strong channel draining across the Denman Glacier grounding line and a bit of a weaker, more diffuse channel draining across the Scott Glacier grounding line, which is just right down here. Over the floating ice shelf in that rainbow color, we have melt rates, where the left-hand side is our parameterization, and the right-hand side, or the middle, sorry, is the satellite observations. And so in general, by using ocean conditions that were observed from tag seals just outside of the Denman ice tongue, we're able to now match the melt rates that we observe in the satellite imagery. And so, yeah, for Denman, we are able to resolve that 126 meter per year maximum. The spatial distribution isn't quite right, of course. You'll notice that in the satellite observations show just a plume of high melt rates, where our parameterization has it a bit more distributed across a wider area of the grounding line. But in general, for a simplified parameterization, we were pretty happy with it. And then near Scott, of course, there's not a lot of melt going on, as you can see, but on the right-hand side of this figure in this red shading, what we're showing are the melt rate enhancements from subglacial discharge. And so for Denman Glacier, subglacial discharge contributed about 60 meters per year of the total melt signal, which we can see for the parameterized melt is about a total of 120 or 130 meters per year. So what that means is that the subglacial freshwater is accounting for about half of that total melt signal near Denman Glacier's retreating grounding line. For Scott Glacier, again, the melt enhancement's a bit less, but that's partly expected because that subglacial channel is just carrying a lot less freshwater, so there's not as much forcing there. And so we published these results just this past October in Science Advances. They were accompanied with some projections of Denman and Scott Glacier. So I'm actually not gonna go over those. I will spoil it by saying that subglacial discharge did accelerate the retreat of these glaciers into that deep upstream trench. But I'm going to focus most of the rest of this talk on some, I think they're cooler projections of a large sector of the Aurora Subglacial Basin. But in terms of this work here for the parameterization, we built a one-dimensional parameterization from previous plume modeling results that resolves ice shelf melt driven by ocean and subglacial discharge. We extended this into 2 dimensions, so it can now be used in a fully dynamic ice sheet model. And for Denman Glacier, we were able to resolve those high rates of basal melting. And I think that the really exciting part about this work now is that we now have a tool that can couple an ocean model, an ice sheet model, and a subglacial hydrology model. And so this is definitely, it's a new tool for the ice sheet modeling community. And I think that it opens some doors now to begin understanding how subglacial freshwater might drive change of the Antarctic ice sheet. And so on that note, I want to get to the next part of my talk now, which is going to be taking this new tool that we created and using it in future projections. And so I wanted to show this figure again, just to reorient ourselves with where we are. So the development of the parameterization, we based it on Denman Glacier up here. And so the rest of the talk is going to be based on an extensive part of the Aurora Subglacial Basin down here. And so this part will contain, the part of the Aurora Subglacial Basin contains some really, really dynamic glaciers that have been changing pretty extensively over the past few decades. And as you can also see in this figure as well, this area is inferred to have a really dynamic subglacial freshwater system as well. And so in this figure here, we're showing the surface ice velocity of some of the glaciers that we're going to be modeling. So in particular, we have a few smaller glaciers up here that in total, when combined, they're called the Vincennes Bay region, and they contain about 0.6 meters of global sea level potential in ice. Then these glaciers wrap around this ice rise law dome, and then we get to one of the giants of East Antarctica called Totten Glacier. So Totten Glacier contains about 3.8 meters of global sea level potential in ice. And most of where you see this red shading is a floating ice shelf. So has a very large ice shelf that supplies backstress to the upstream glacier. But this one it's the largest ice discharger in East Antarctica and has been undergoing rapid changes. And then down here, we also have Moscow University Glacier, which contains about 1.2 meters of global sea level potential. So this area of Antarctica is massive and like I said, has been undergoing some pretty rapid changes. And so in this figure on the right, we're zooming into Totten Glacier in Moscow, and we're showing in that red shading our grounded ice thinning rates between 2010 and 2019. And the gray shading denotes the extent of the floating ice shelves that support these glaciers. So near Totten Glacier, right near the grounding line, thinning rates exceed about 1.5 meters per year, which means that the surface of that glacier is lowering by that amount every single year. So it's a very strong signal there. And also as well, this is located right along Totten Glacier's main ice stream. The grounding line in this location has retreated about 3.5 kilometers since 1996 and 2013. And for Moscow, this glacier has also been retreating and thinning as well. So as I said, it's a very dynamic area of East Antarctica. And it's known that warm ocean waters circulate on the continental shelf here and drive rapid rates of ice shelf basal melting. In the previous figure, we also showed that there's likely a really dynamic subglacial freshwater system that could drive dynamics here as well. And so all of this is just a ton of motivation to say, what the heck is it going to do in the future? And we think it's a really prime candidate for this type of study. And so ultimately, with this work, to resolve what's going to happen in the future, we need to develop a coupled ice subglacial hydrology model. And with this model, we're going to resolve two freshwater forcing processes on ice dynamics. First, I wanted to start with, this is going to be our model domain here. So right, you can kind of be oriented with where we were before showing the ice velocity, but now you can see the inland extent of just how far these glacial catchments reach. And it's, so this area is really large and also contains a lot of ice grounded below sea level, which makes it naturally vulnerable to warm ocean waters. And so with this model, we're going to resolve the enhanced ice shelf melt that results from subglacial freshwater that drains across the grounding line. And here is just the present day model setup where we simulate subglacial freshwater channels draining across the heads of every single glacier in our domain. For Totten Glacier in Moscow, these channels carry pretty significant amounts of water that result in pretty strong melt enhancements. And then for Vanderford and also the ear canal of Totten, which is located right over here, there's some lighter channels that do enhance melt, but it's just really small that you can probably barely see it. Another process that we're going to resolve here is how subglacial freshwater that builds up beneath the ice sheet can essentially lubricate the base of the ice and make it slide faster. In our ice sheet model, we compute friction in a way that it's proportional to the pressure that the ice exerts on the underlying bedrock. And so when there's no subglacial freshwater, our friction is just proportional to the pressure that the ice pushes down the bedrock. But as subglacial water builds up, it actually opposes this pressure. And that reduces the frictional force of ice sliding along the bed. And that means that the glacier can flow more easily towards the coast. And so these are the two processes that we're going to resolve with this model. And then I just wanted to show how we end up coupling these models. So we have our subglacial hydrology model on the top here. We use the glacier drainage systems model. On the right, this is going to be our ice sheet model. So we use the NASA-funded ice sheet and sea level system model. And then in the middle is our ocean melt parameterization. And then on the left is just some ocean model output that we use to drive these projections. So in the first coupling step, what we're going to do is run the subglacial hydrology model forward to obtain the channelized subglacial discharge flux that will feed into the melt rate parameterization. We also have the ocean model output that is used as an input as well. In the next step, we use that parameterization to compute a melt rate field that drives the ice sheet model. And then we pass the effective pressure from the subglacial hydrology model to the ocean model as well, to the ice sheet model. So that's how we resolve those two processes. And then the next step, we run the ice sheet model forward to catch up. And then we pass back all the necessary fields to the subglacial hydrology model. We keep running in this asynchronous manner out to 2100. And so that's how these two models end up interacting with each other. So for these future simulations, we run them from 2017 out to 2100, and we run a low emission, high emission ocean forcing scenario. So on the figure on the right there, you're seeing the time series of ocean temperature for the low emission in blue and high emission in purple. So we can see we're running from 2017 out to 2100, and then on the y-axis is just the ocean temperature in degrees Celsius. So you can see for the high emission, we have a pretty steep ramp up in ocean heat after about 2050 or so. For each ocean forcing scenario, we run 4 experiments. The first is just an ice-only experiment where we don't resolve any freshwater feedbacks. In the second experiment, we change frictional drag according to how subglacial water impacts the effective pressure, right? So that's just a frictional experiment. In the third experiment, we include that subglacial discharge melt enhancement. And then in a fourth experiment, we include both processes. We're just building our experiments in terms of the processes that are resolved up until we finally include everything into that fourth. So that's 8 simulations in total, 4 low emission, 4 high emission. And in this talk, I'll mainly focus on the high emission, but you will see the low emission a bit. And so this figure here is showing how the subglacial environment and also the grounding line in our model evolve from 2017 on the top left down to 2100 on the top right. So the main idea I wanted to get behind this figure is that in 2017, we do have an active subglacial freshwater system because you can see the channels there draining across the grounding lines, but this environment really ramps up by 2100. First in the number of channels, right? So we can see that there are many, many new channels that have formed along the grounding line that don't exist in the current model state. In addition, these channels now extend much further distances inland and also carry a much more considerable freshwater flux. I think the strongest channel draining into the head of Totten has a freshwater flux of over 70 cubic meters per second, whereas in the present day, it was maybe about 20 cubic meters per second or so. And so ultimately, this enhancement of the subglacial environment is going to drive change in the ice sheet model relative to the ice-only experiment. And so in this next movie, I'm going to show how the grounding lines in our 4 high emission experiments evolve. And so the legend for how the colors relate to the experiments is up here, where brown is the ice-only experiment. And then this bright pink color is going to be our projection that resolves all the freshwater processes. On the right, this is going to be focused on Moscow Glacier. In the middle is Totten Glacier, and then on the right is Vanderford Glacier, where the time of the projection is located on the upper end of the Moscow panel. And so focusing our attention first on the head of Totten Glacier here, and this by about 2030, both of these experiments that resolve the melt rate enhancement unground. And this is, again, along Totten's primary ice stream. It's not until about 2060 or so that the experiments that do not resolve this melt enhancement dislodge. In addition, like focusing our attention now on Vanderford, you'll just notice large discrepancies in the positions of the grounding lines between the experiments, where between the ice only and the fully coupled model, the discrepancy can be on the order of 7 to 10 kilometers, which is quite significant. And so ultimately with this, we're getting an understanding that these subglacial meltwater feedbacks can accelerate the retreat of Antarctic grounding lines. In terms of the sea level contribution from this domain, here we're showing all of the experiments. So this is going to be a time series from the time series. So we have time in years on the bottom, and then the total cumulative sea level rise equivalent on both y-axes, where on the left is millimeters and on the right is in units of gigatons. So all of our low emission experiments are colored in the cool colors, and then warm emission, high emission is in these warm colors. And so with this figure, there's two main points. The first is that overall, the largest uncertainty in the simulation stems from the ocean, right? So you can see the large difference between where the cool colors are by 2100 and where the warm colors are. It's almost an 8 millimeter global sea level potential rise difference. With that being said, though, the difference between the different experiments in the high emission and the warm emission, high emission, the low emission are quite strong as well. So for the high emission scenarios, right, the difference between that brown line, which is our ice only experiment, and the pink line, which is our fully coupled model, it's about a 30% increase in the global sea level rise potential from our model. And so ultimately what this means is that these subglacial processes enhanced the sea level contribution of our domain by 30% under high emission scenarios. And so this paper is currently under review in JGR Earth Surface, so hopefully it comes out soon, fingers crossed. And so essentially what we did was we took that new parameterization and implemented it in century scale projections of the Aurora Subglacial Basin. We found that grounding line retreat was accelerated by the subglacial environment, and then mass loss was also accelerated as well. But the ocean, of course, is still the primary source of uncertainty. So going back to this figure, ultimately, we understand that the subglacial freshwater isn't just isolated to this sector of East Antarctica, right? It's been inferred to be widespread across the entire Antarctic ice sheet. We found that this freshwater can accelerate grounding line retreat and mass loss from glaciers. And so it begs larger questions. The first is that the Antarctic ice sheet is essentially booby-trapped with tipping points in grounding line retreat, kind of like what we saw for Denman, where there's these very strong destabilizing trenches that exist in all of these different subglacial basins around the continent. You know, if subglacial freshwater can accelerate grounding line retreat, is it then possible that these feedbacks could lead to faster than projected collapse of large sectors of the continent? In addition, we found that mass loss was accelerated as well, but all of the assessments of the Antarctic contribution to future sea level rise have mainly been ocean driven. They haven't included the subglacial environment. And so with that, is it possible that we could be underestimating quite significantly the contribution of Antarctica to global sea level rise? So these are the big questions that I think comes from this more focused work. And then it kind of leads me to where I want to take this. And so ultimately, we're trying to answer some of these questions now. So we have some work that's in progress on a few sectors of Antarctica. We've seen some of the work that's ongoing in the Aurora Subglacial Basin, but I'm also spinning up a project with some collaborators at Dartmouth to try to understand how these feedbacks could drive change of the West Antarctic ice sheet, which, as probably most of you know, is a bit more unstable than East Antarctica. In addition, we also have work going on to use similar modeling techniques to simulate sounds and glaciers in the Arctic with relevance to other icy ocean worlds as well. We also have a funded proposal where we're starting to spin up the work as well to, again, use these modeling techniques to try to understand radar signatures underneath Antarctic ice shelves, to see if we can get an idea of what these radar returns mean on other icy ocean worlds as well. And then lastly, we have a bunch of proposals that currently undergoing the review process to try to extend our knowledge of how these freshwater forcing processes can drive change of other Antarctic basins. So some areas of interest that we haven't started working in yet are the Wilkes Subglacial Basin, which is possibly another weak point of the Antarctic continent on longer timescales, the Amundsen Sea sector, and then we've also proposed to try to model the entire Antarctic ice sheet using these coupled models as a proof of concept. In addition, so that's a bit more short term. In the long term, I'm really interested in understanding interactions of the ice sheet with, again, the subglacial hydrology system, but also with the atmosphere. In particular, on longer timescales, we understand that as surface temperature is warm, this is going to lead to surface melting of the ice sheet that could drain to the bed and feed the subglacial water system. If this occurs over floating ice, this could also lead to ice shelf disintegration. And so this is another process that hasn't been included in models, but with the coupled modeling that we've developed, we think that is probably possible to start working on. In addition, we can use these modeling techniques to start understanding biological productivity on the Antarctic continental shelf, and in particular, how subglacial freshwater and the nutrients that it carries could feed productivity systems. And then there's also, again, continued ice-ocean interactions. So as we saw, the ocean is still the primary driver of uncertainty. And so I think work into understanding how the ocean interacts with the ice is, I don't think it's ever going to go away. And so I'm still very interested in working on those fronts. I'm also interested as well in the inverse. So not just on how the ocean interacts with the ice, but also how a changing ice sheet might drive change of the surrounding ocean as well. Because we can use fully coupled ice-ocean models, we can investigate both. And so I think that that's a really exciting avenue for future research. Lastly, on a note that's a little bit different, I want to continue work that I've started up with the ice sheet model intercomparison projects. So these are very large-scale international collaborative works that combine over 36 international modeling groups to try to develop ensembles of sea level estimates of Earth's ice sheets. And in particular, I've been working on the Antarctic focus of this. And so we've just finished up ISMIP-6, which was following up CMIP-6. And so we currently have a project to try to extend simulations out to 2300 for the Antarctic ice sheet. And so that paper should be coming out pretty soon. And so this is one of the figures from it, just showing the percentage of models in the ISMIP ensemble that project retreat of the Antarctic ice sheet by 2300. So with these really big ensembles, instead of just running one ice sheet model, we can start to run statistics on a diversity of models. So essentially what you're seeing here, in essence, is like a potential for a collapse of the Western Arctic ice sheet by 2300. And you can also see large sectors that are projected to retreat with high certainty. I'm planning to continue leadership into ISMIP-7 as it starts getting going and in future opportunities. And so I think that it's a really wonderful training opportunity. It was my first introduction to the international ice sheet modeling community. And so it's something that I would love to bring to UTIG. And so with that, I just want to thank my collaborators, in particular. So Jamin Greenbaum worked here for quite a long time. So he's my current postdoc mentor. So he's been really fundamental in a lot of this work. And then there's a long list of mostly modelers that have helped me along the way, and also some funding sources. And so, yeah, I'd just like to thank you for all your attention, and yeah, happy to take any questions.
right. Thank you for a great talk. We can take any questions.
Hi, thanks Taylor for great talk. It's really exciting what you're showing in terms of, you touched on how all this complex system will affect sea level rise, which is by itself an important issue. But also you showed in your models that first you have in the 1D and 2D that somewhere you get a freeze afterwards. But then your 30%, you said that in the high emission, gradually you get increased to the highest scenario. So I'm wondering first, between those complexity that you're adding, what is the uncertainty on each step in the overall? But also another pivotal question is how can you extend that? Because obviously the emission or the long term until 2100, how do you extend it when you know the feedback loop of how it's going to accelerate the melt? Because then you're going to have isostatic rebound, oxygen and nutrients, which kind of interact with methane transformation, CO2, carbon. Is that accounting for that?
Yep. Yeah. Thank you for the question. So I guess for the first part of that, you're right. The uncertainties definitely compound as you move forward with trying to extend from 1 dimension to 2 dimension. I think that the major sources of uncertainty here are that the subglacial environment is extremely challenging to observe. And so, I think our parameterization does have uncertainties in it, of course, because it's so simple. But I think in terms of the projections, getting constraints on exactly how much subglacial water is currently flowing beneath the ice sheet, where this water is located, and then furthermore, just ocean temperatures in the continental shelf as well. I think for Taunton Glacier, we have a pretty good idea, but elsewhere along the Antarctic continental shelf, it can be a bit more scarce. And so I know that there's a lot of like highly collaborative observational work that's being done here at UTIG to try to address some of this, in particular flying ice penetrating radar over the grounded ice sheet. That way we can start to infer where locations of subglacial water might exist. And so there's definitely active fronts to reduce this uncertainty, but uncertainty also compounds as you go into the future as well. And so, yeah, it's a great point. In the paper that we submitted, I think we spent about like two or three paragraphs just talking about uncertainties and trying to move forward from it. But it's definitely a tricky aspect of this work. In terms of the climate forcing itself, you're right. So we use so for the ocean model that we used to extract those conditions, it was forced by CMIP model output. And so I think for the most part, CMIP it resolves changes like in carbon and the atmosphere and everything like that. But our ocean model itself can only react to the boundary conditions. And so those ocean model outputs don't, for instance, they don't include a changing ice sheet right now. It's just like a static one-way coupling. But we're able to extend that out into the future by forcing with CMIP. And there are some CMIP models now that extend out to 2300. So if we wanted to extend for longer time periods, we could, but I think that's about the end of what we could do using realistic forcing. I think after that, we'd have to use something more idealized if we wanted to look on like real glacial timescales.
Great talk, Tyler. I guess my question's also in the uncertainties, but it's at the bed scale, in the sense if we look in the Aurora Subglacial Basin offshore, or I guess the output from that basin, there's a transition in the sedimentary facies, right? We go from something that looks like modern Antarctica with very polar, very little bits of sediment to something that looks like there's a lot of water and very large movements of sediment. In that, is there a boundary condition change that is either in any of these models or could be added to the models where sediments get into this in a big way at the base and could actually have a potential negative feedback or positive, whichever way it goes?
Yeah, no, it's a great point. Yeah, we don't include that in our model, but I think, yeah, it would definitely take a lot more model development right now. I don't think with the current capabilities it's possible, at least in this model setup. But I think to try to test that, we would have to use the full cavity resolving ocean model. And then at every ice sheet model time step, we could probably change the bed, like increment the height of the bed a little bit to, I guess, like what we would expect from the observations. And that's one way we could try to move forward with experimenting with that numerically. But I think because we're using the parameterization that covers the entire sub-ice shelf cavity, we wouldn't be able to do that in this three-way coupled model. We might be able to do it for shorter timescales with the fully dynamic ocean.
Hello, thank you so much for a really good talk. I have a maybe slightly technical question that you maybe covered, but I missed it. So in your kind of simple parameterization, you have two equations and then a cutoff. Is that a hard cutoff, or is there some kind of gentle merging of the two things, and how do you do that?
Yeah, so it's a bit of like it's a bit interpolated between, I did leave off the part, like a part of the equation that does that just for simplification, but yeah, I forget the exact equation in my head, but it is a smooth transition where we essentially interpolate what we have from the end of the meltwater regime and interpolate it into the ocean regime. The discontinuity between the regimes is not very big. And so there wasn't a ton of work to be done there. So, but yeah, we did have to include a bit of interpolation.
Thank you very much.
Of course.
Yeah, thanks. Really great talk. And another question on the parameterization. So it looked like there was a bit of an undershoot on the freezing side for the equations. Do you have a sense of why that is? And was there any case where freezing would matter for the kind of work that you're doing?
Yeah. These plume-based parameterizations have just never handled refreezing quite well. I will be honest, I haven't looked into it too much. I've always been worried about the stronger melt. Yeah, in terms of whether or not it matters, I would say on these longer timescales, probably not. But I think there's short timescale work right now that we're trying to do to understand like how radar signatures of refreezing and melting, like how that might relate. And if we can like try to work back ocean processes from that. And so I think on these smaller timescales where we're doing our process-based studies, that can be extremely important. So yeah, it's definitely taking more of a look into, but yeah, with this longer timescale type of work, I haven't quite done that yet.
Any final questions? If not, oh, in the back.
So just a quick question about the models that you use. Are you interested in the three? Oh, I talk with my hands. Do you have three-dimensional volumetric data for underneath those ice shelves? And are you interested in any of the individual processes that are going on there? Are they related to the science that you're looking at?
Yeah, definitely interested in it. I think in this work, we tended to smooth over a bit of those processes because of the long time scale. But yeah, I'm absolutely interested in these more process-based studies to essentially like understand where the meltwater goes, where exactly the fresh water is going to flow. And of course, that's going to be more of a function of the ice shelf geometry itself. So I think it kind of begs that we need a bit more data probably to understand those processes. But I think with the fully three-dimensional ocean model coupled to an ice sheet model, that's yeah, something that we can start to look into, and I think it would be really exciting.
Okay, so your ice sheet model is it? So I work with the E3SM folks, and I know they're working on coupling the ice sheet model with the ocean underneath, but they're not quite there. They told me another 6 months. Are your models coupled or not yet?
Mm-hmm. Yep. Yeah. So the ISSM and the MIT GCM, we've coupled them. We've coupled them offline. So it's like an asynchronous coupling where we run the ice sheet model first and then the ocean model to catch up. And for the ocean, we use some like a temporal averaging of the conditions to drive the ice sheet model. So it is coupled offline. I'm not sure in E3SM if they're trying to couple online, but yeah, we have managed to do that, and we have a few publications for both East Antarctica and West Antarctica as well. So yeah, there's some proof of concepts for that as well. Yeah, thank you.
Okay, thanks. And I think we should just wrap up and thank Tyler again for a great talk.